Hello and welcome. I'm Pravir, and today's session is leveraging causal models to craft AI strategy. Now, to begin, I'd like to draw attention to this Gartner hype cycle for artificial intelligence for 2022. And if we pay attention to the category causal AI, we'll see that as per estimations, it's expected to mature within 5 to 10 years in 2022. Now, if we look at the hype cycle for artificial intelligence in 2023, then we'll see that the same category is now expected to mature in 2 to 5 years. And this dynamic is captured very well by a quote from Pope John Paul II: "The future starts today, not tomorrow." And that's precisely what I want to draw attention to. Causal AI is extremely, I think, important and critical as we begin to develop AI systems, simply because we need to embed different kinds of thinking, meta knowledge beyond what machine learning and LLMs can provide. And therefore, the need for something like causal AI is very important as we move forward. And this presentation is all about how do you create causal AI systems. So I want to start with a introduction to some systems thinking foundations. So particularly looking at archetypes, and I'm going to draw attention to two archetypes: limits to success and fixes that fail. I want to draw attention to the idea of developing causal AI, which is all about moving from weak to strong AI. And in this, I'm going to dive a little bit into causal models, into mental models, into the idea of meta-knowledge. And then importantly, if we're going to build causal AI and leverage models, what becomes critical is the validation of the model. And so I'm going to draw attention to three kinds of validation that are referred to as epistemic complexity, resolution complexity, and validation complexity validations. Finally, I'll summarize and conclude with an overview of lessons in crafting AI strategy based on consulting work that I've done over the last year and a half. And since the default thinking is that this kind of causal model approach to AI is perhaps the province of large organizations, I want to also draw attention to the fact that it's in fact very applicable to small and medium-sized businesses. So let's start with some systems thinking foundations. And I'm going to use a simplified depiction of supply chain management. And here's a simple causal loop diagram where we see two loops. One's a reinforcing loop and one's a balancing loop. And let's go through the logic of this. So if we start at this common node, which is sources of supply, as the sources of supply go up, then the inventory is going to go up. And so we see a positive correlation there. As the inventory goes up, generally to reduce the inventory, the price is going to have to go down. So there's an inverse correlation there. As price goes up, then in general, there's an inverse correlation with demand. So demand's going to go down. So there's a negative correlation there. When demand goes up, then there's a positive correlation with need for supply. And when need for supply goes up, there's a positive correlation with source of supply. So what we have here is, if we look at the net of these positive and negative correlations, the negatives cancel each other out. And so you've got a net reinforcing loop, which suggests that the source of supply is going to continue to increase, the need for it is going to continue to increase given this dynamic. And we can perhaps call this new product growth. That is, of course, something that many organizations and companies would want. Now, however, this reinforcing loop is being balanced by the supply chain vulnerability loop. So that's the second loop. So if you go through the logic here, as sources of supply go up, then generally we can say the geographic spread would go up. So there's a positive correlation. As the geographic spread goes up, then the transportation distance is going to go up. So there's a positive correlation there. As the transportation distance goes up, then the likelihood of supply chain disruption happening is also going to increase. So there's a positive correlation there. And as supply chain disruption increases, then the likelihood of source of supply going down is going to happen. So there's an inverse correlation. So when we look at the net of this, then we see that there's a overall negative over here, which means it's a balancing loop. And it means that if we consider both these loops in union, that the new product growth will never really fructify because it's always going to be dampened by this supply chain vulnerability that's a reality for this dynamic. What this archetype, this is a common archetype, and it's referred to limits to growth. And if we look at its behavior, then essentially over time, the time axis, the x-axis, and this is some arbitrary growth indication on the y-axis. And so what we see is that the new product growth will go up to a point, but then the supply chain vulnerability, which is also going up, is going to kick in, and then it's going to change the nature of the new product growth so that it begins to take a downturn. And so managing this kind of causal loop diagram becomes important. Now, when we link this to AI, what's important to consider here is that if we were to focus AI, as is the case today with many of the tools that we're seeing, these may be focused on any single node over here. And so there's some local optimization that's happening, but this local optimization doesn't take into account, obviously, the systems picture. And so it will lead to constraining factors. It will lead to this reality of limits to growth, which will probably get accelerated because of the use of AI tools that are just being used locally instead of considering the underlying logic, the system of causality that's driving this particular aspect of the organization. Now, this leads us to another kind of archetype that we can call fixes that fail. And using the supply chain vulnerability, the causal loop diagram with the limits to growth all embedded in here, there's another system of causality that often happens in organizations that refers to an archetype called fixes that fail. And the reason why it's a fix that fails is that when a problem occurs, and here it's a supply chain vulnerability, then in order to solve it, there's an impetus, so there's a positive correlation to go more local. But when we go more local, then immediately the supply chain vulnerability decreases. And so what we see here is a balancing loop, and this is the kind of behavior we want if supply chain vulnerability is the focal point. However, what's not considered is that there's often a longer term effect, because when we go local, then in fact, we're reducing the resilience of the supply chain. And so there's a positive correlation between going local and reducing resilience. And when we reduce resilience, as this goes up, that is that as resilience gets further reduced, then the supply chain vulnerability is going to increase. And so there's a positive correlation there. And if we look at this system, this larger system here, then it's a reinforcing loop. And so what's happening is that if we look at the behavior, then in fact, the problem symptom is never going to decrease, but in fact, it's going to continue to increase. However, when we apply whatever patch we're applying, in this case, go local, then immediately we're going to see a dip in the problem symptom, and it's all going to look nice and dandy, but then over time, it's going to become worse than it was. And this is a reality, again, that happens at a lot of different organizations when you look at the system of causality. And again, if we're focused on optimization of parts of these causal loop diagrams, which is often the case, then we're never going to truly move the needle in the direction that we want to over the longer term. And that's the point of considering causal loop diagrams. Now, other common archetypes, and I'm not going to go into these in detail, but there's something called success of the successful, where it's a it's a self-prophesying, a self-fulfilling prophecy rather. So if there's two projects in an organization, to draw an example, and there's one project that appears to be doing really well, and the other one that doesn't appear to be doing well in the short term, then we would tend to send more resources into the project that's doing well. So there's a reinforcing loop there, and that project is going to continue to do great. And since we've cut resources from the other project, it's going to continue also in a reinforcing loop, but continue to go worse and worse. And the point here is that unless we're aware of dynamics like this through mapping out causality, then we would miss this kind of marginalizing effect that's happening across the system of causality for an organization. There's other common archetypes, and I'll consider one more. So here you've got something that happens, again, very commonly. It's called drifting goals. You have a goal for an organization. You have the actual results. And the way that we tend to address it is that if we don't meet the goal, then we reduce the goal. And so this sets into motion one set of balancing loops. And then in reality, what we want to do is that we want to truly address the fact that we're not meeting the goal we have rather than change the goal. We want to put into place, which is always more expensive in the short term, permanent fixes that will change these dynamics. However, what happens here is that we in fact shortchange ourselves because our attention and our processing power goes to, in fact, create goals that are less and less meaningful over time. There are many other archetypes. In fact, MIT had come up with the system first, perhaps in the 1950s, with their discipline of systems thinking. And they had also surfaced a number of different archetypes that I think there are 13 or 14 of them. And there's more. As we do work in areas, we find different kinds of archetypes that have not necessarily been considered. And the point being is that it's important to pay attention to these and to have a system whereby we can actually surface them so that we're approaching AI in the right way. So now the question is, having considered that, how do we move from weak to strong AI? So in general, the way to think about weak to strong AI is that weak AI is perhaps where we use machine learning, where we use LLMs, and these tend to be domain specific, and we see immediate results. We may see revenues increase, we may see costs going down, and there's a short-term euphoria where we tend to do more of the same thing. However, that's a trap. And what we really need to do is move to a system of strong AI, where we're looking at the system of causality for an organization by beginning to build causal and other models. And so the scope becomes general, and I'm going to give a few more detailed examples of this. And the other critical thing as we move towards strong AI is that we have to get away from just empirical type of data. So with events and conditions, or with data analytics and machine learning, we have to move to the realm of modeling using non-empirical mathematical heuristics, using meta-knowledge. And I'm going to give examples of, especially of these three upper layers here in building strong AI and moving towards what's called causal AI. So when we consider models, as I've suggested, there's causal loop diagrams are a great first place to start with any modeling efforts. And here, for example, we have a goal for the organization, and then we systematically try to understand what all the different, or the logic that's impacting that node that extends beyond linear logic. So there's what we can discover as we understand all the interactions by observations, by interviewing people, is that there's a system of causality that this organization is subject to, and there's many different things that need to be considered to actually affect this goal over the long term. Another kind of model is that I've used extensively is agent-based modeling that I like to use because it allows for a lot of diversity in thinking. It allows for simulations that mimic real world situations in my estimation more accurately than perhaps other kinds of modeling. And whereas the causal loop diagram is telling us theoretically what the system of causality is, when we build simulations that are based on this, then we can actually see, if we use real data in here, which I'll be speaking about soon, we can see the actual effects of changes that we're making to this causal loop diagram. So what's also important to consider, especially if we're working with a complex organization, is the fact that there's going to be variations in causal models. And here's a, a scenario where an organization that I was working with had many different divisions. When we asked key decision makers in these divisions what drove the factor that we were trying to optimize, we came up with literally a unique model for each decision maker. And that's the point. So there's variation agent causal models, but we want to be able to make sense of this. And this gets into this aspect of the mathematical modeling as well, because we have a model that begins to surface the diversity in thinking, but then the question is, how do we embed that into our agent-based or other simulations that we might be creating? And so here, this is just showing a way in which it begins to get mathematized so that we can embed it and it can begin to impact different scenarios, different levers or strategies that we might employ for the next 2 to 5 years. And basically what you see here is that for several different departments, there's components of the causal model that were called out, and we see the strength of that component by department. And so we have an overall picture of how causal model components vary across different parts of the organization. And then we can take an average for each department or each division, and that then becomes something that we embed into our model, because we can hypothesize that this average approach is what's tends to create the average results. And then we can also begin to see that if different division or department is driving something, how the causal model might vary, or how the results might vary because of the way that they're approaching things differently. So that addresses this idea of variation in causal models. And then also another thing to consider that's very important is mental models. So if we again consider, so along this axis or realm here, a range of different mental models, and here, if we consider different divisions or units in a complex organization, we can begin to see how key decision makers for similar decisions employ different mental models, different ways of approaching problems. And we can even begin to see what the variation of mental models across the organization are. And we can, for example, if we're looking at a particular part of the organization, we can begin to isolate conflicting mental models, which again becomes important when we're trying to make process changes or we're trying to actually implement strategy. And we can mathematize this again by looking at the commonality of particular models within a part of the organization and make suggestions, or rather mathematize what's more strongly used in terms of the default approach at a division, or in terms of which model tends to be used more, which becomes important again when we're trying to predict things accurately, different process changes, strategy changes, cultural changes, and so on. It's important to have a picture of this aspect of causality that subtly drives things. Now, that leads us also into the next category of layering of quote unquote data, which is meta knowledge. I had referred to already this causal loop diagram. But when we look at this causal loop diagram, there's a lot of interesting insights that surface because of it. And for instance, if this is the key objective for the organization and we want to impact that, then we know that since the direct links between different causal loops that occur around this key objective are more, that if we work on projects or AI along this realm here, then we're going to impact this goal more powerfully than if we were to work on projects that are further away from this objective, because there's a more intricate system of links that goes from here to here, and the effects that or changes made here may peter out, or may not have as strong as an impact as changes made in this realm over here. And so that's one type of meta knowledge. And then a second type of meta knowledge is where we pay attention to the different archetypes. And I had mentioned a few: limits to success, fixes that fail, success to the successful, drifting gold, and so on. So we have to look for these kinds of marginalizing archetypes that are occurring in the causal loop diagram. And this, again, is important because if we can recognize these different archetypes, then we can also change them. We can inject different kinds of AI to change the nature of these loops so that they don't become compromising or marginalizing. And that really is how AI should be proceeding, is by recognition of the meta knowledge that's driving the organization in a particular way and surfacing that and then addressing it at its root. There's other kinds of meta knowledge that is equally important, and they all derive from the system of causality captured by causal loop diagram. I'm just going to draw attention to a couple of these. For example, in this system here, what we have is a really great example of a nonlinearity, where it's found that this small area of the causal loop diagram with its loops has an overwhelming impact on the rest of the organization, the rest of the processes that define how the organization does its work. And so if we begin to make changes here, then it can have a huge impact on the rest of the system that animates the organization. These diagrams here refer to something that I had just called out in the previous slide, and that is that once we recognize an archetype, we can also fix it. We can change the nature of loops by introducing a new loop that would, for example, change forever limits to success or fixes that fail. And AI needs to happen or kind of occur here where it's actually changing the nature of the loops. If we look at this aspect of meta-knowledge, then what it's suggesting is that there's a particular function or denomination that's common across many different areas of the causal loop diagram. And if we create AI that can address this underlying dynamic that's occurring in several different places, then again, we can have a huge impact. And this one is drawing attention to different kinds of organizational changes that, rather organizational dynamics, organizational development, that if we were to develop AI that addresses these, then this is the kind of impact we would see on the overall system of causality. So now the question is, how do we actually validate a model? So if we're creating a model, if we've got this causal loop diagram, then the question is, if we're going to use this as a foundation for AI, it becomes very important to validate that what we're doing is in fact makes sense. So there's 3 steps to validation. First is the epistemic complexity validation, and this is going to be correlated to the cognitive challenge the overall cognitive challenge that's being faced by the organization. So to put it simply, if there's multiple perspectives, if there's a large amount of interconnectedness, if there's a large amount of dynamism, then we want to have a model that has an equally um, is going to meet this cognitive challenge. And so the epistemic complexity of the model has to be aligned or in tune with actually what the reality of the organization is. And so we need a system of validation that will suggest that this epistemic complexity is being addressed in the right way. And then similarly, we can create a model that we've now leveraged with the right epistemic complexity, but the question is, how do we resolve this? So there's a resolution complexity that becomes equally important. So even before the rubber hits the road, even before we make changes in practical changes to the organization, is there some way to actually validate this resolution complexity given the model that we put in place? And I'm going to speak a little bit about that. And then finally, there's the practical validation that needs to occur. That's when we've got these models in place and they're predicting or they're suggesting that particular changes need to happen or particular AI needs to be embedded in an organization, then we need to be able to practically validate it, that in fact what's being suggested is showing results in, say, 6 months to 18 months, and we need to adjust our models if things aren't being predicted accurately. So let's look at epistemic complexity in a little more detail. So this is all about the right modeling. And when we think about moving from weak to strong AI or causal AI, then I want to make the case that many of the things that I've pointed out, they're going to be required to get to a model of right epistemic complexity. So we're going to have to consider the system of archetypes of causality. We're going to have to consider mental models. We're going to have to look at variations in causal models. We're going to have to develop a scheme to actually surface meta-knowledge and use that to make changes. And the more the epistemic complexity, the more we want to actually drive to these kinds of modeling mechanisms, if you will. Now, the other thing to also consider is if a model has a high epistemic complexity, then we want to consider what is called the fragility to anti-fragility continuum. Now, fragility of an organization can be thought of as a state in which systems are damaged by disorder and stress. And clearly we want to veer away from that. A resilient organization is one that, or a resilient system is one that has the ability to recover from failure. So it's had problems due to unexpected inputs, but then it's able to turn that around. A robust organization is one that simply can, from the get-go, it has the ability to resist failure. And an anti-fragile organization can be thought of as a property of systems in which they increase their capability to thrive as a result of any kinds of stressors, shocks, volatility, noise, and so on. And depending on the level of epistemic complexity, we certainly want to be able to either make sure that our models that are creating have this resilience at the very least. And then if it's even more complex, then we want to get to robustness and anti-fragility. And so as, for example, as we're looking at different levers that we want to make changes with that are a result of the model that we've created, we want to ask, what do those levers do in terms of moving us along this continuum? So here are some levers that move us out of the state of fragility. Here are some examples from a past project of levers that strengthen resilience. Here are levers that strengthen robustness, and here are levers that strengthen anti-fragility. And it becomes important to recognize when we're making changes to a model or when a model is predicting something, that what actually is its impact on the continuum of fragility to anti-fragility. In fact, can we create levers that would ensure that the organization becomes anti-fragile, especially if it's operating in a very complex environment? Now, when we get to resolution complexity, then many of these devices that I've already introduced have to be used as inputs into simulations that we create. So resolution complexity is going to be addressed by creating a simulation that not only shows the results, shows why. So we want to be able to create a model that, if you were to turn the clock back, it would show us why the organization had the results it did last year or the year before. And so there has to be an accurate read. And then similarly, as we project forward, we don't have the results yet, but if we can validate that the model retroactively predicted the right results that the organization actually had due to the modeling that we've done, then our confidence in its resolution complexity is going to increase. Now, if we've got an organization with a high epistemic complexity, then basically we want to be able to also have this ability to validate the resolution complexity. And here there's this depiction of an agent-based model, and there's 3 different agent populations. We can think about this as, for example, different roles that interact within the organization, the key processes or steps in a key process we're trying to change, and then the variation that different units or divisions might have on how they do things. So we're considering 3 kinds of populations here, and then each of these is embedded with its own heuristics, its own way of seeing things. And we don't know how it's all going to play out, but we've embedded as much intelligence as we can from the devices, from these and other devices. And to the degree that we're able to do that, then the resolution complexity can be better validated. So that's what I spoke about, the resolution complexity. But then the question is, what's the actual process for going through the validation of resolution complexity. So we have, as we look at this agent-based model, as I said, these are three different populations. And then we can think of these golden nodes as different strategies that impact particular populations. And then we have scenarios that are combinations of different strategies. So what we want to do is we want to be able to run different scenarios, and we may run thousands of scenarios. And then we want to check the impact of the scenario based on a metric that we've created. And in this case, let's just assume that important aspects of this metric are cycle time to, say, deliver milk across the country, and the anti-fragility of the organization. And we want to test each scenario against its impact along this combined metric. We then take winning scenarios and we want to test them in different market types. So in different market types. So we want to test them in a normal market type, in say one that is a recession, one in which there's inflation, one in which there's a lot of aggressive growth. So we just take different scenarios or different contextual dynamics of the market, and we want to test all our scenarios to make sure that they still move ahead. We then want to create a winning roadmap project portfolio. So we have these scenarios, and each of these scenarios is, as I said, made up of different strategies. Each of these strategies would need to be implemented by a specific set of projects. So we take our winning scenarios and we create a project portfolio that's required to actually implement that. We then also take commonalities across the top 5 scenarios, and we create a project portfolio based on that. We then decide on a portfolio that will populate the roadmap. We generate project evaluation for each of the projects that have been selected. I'm going to show that on the next slide. And then we map out the effort required for implementing that project, and then we can slot it into different phases in our roadmap, and then distribute those phases across the roadmap. And so that's how we get to the resolution complexity. So it becomes something that's much more real. We can see the logic that is being suggested when we work this out, and that gives us a higher confidence in the epistemic complexity, that the model is at the right epistemic complexity, and that we have the right resolution complexity also being displayed by the model itself. So when we look at the scenario impact, particularly what we want to do is we want to first work out the boundary situation. So if we have no levers that are actually being, or no strategies that are being employed, then we come up with a lower limit for the impact effect. If we then activate every single strategy, those golden nodes I had showed you earlier, then we come up with a highest possible impact. So we now have the boundary conditions, and then we have different scenarios or different schemes for normalizing strategy across complex organizations. And so now we have typical impacts from that. And then we have a reality lever where we take, many times when we create strategies, then in reality, we can't mix and match all those strategies together, but we take, or we create settings, which is a baseline realistic setting. And so we test what the impact of that baseline realistic setting is. And then we are ready to actually test out the different projects and scenarios. So what we do is we use a generic lever plus, for example, the market focus scenario, we activate that, or we use a generic lever plus we activate customer focus. And then we can see the impact given that complex causal loop diagram that's created the agent-based model. We can look at the predicted impact over a 5-year period or a 2-year period. And so we now run a whole bunch of scenarios and we create or we have an idea of the winning scenarios in terms of the overall impact that it has. And then, as I suggested earlier, we decide on the portfolio of projects, and then we run the evaluations for every single project uh, to look at, to begin to isolate its effort. And so once we have that, then we're ready to create that roadmap that we're talking about that'll help with the resolution complexity. Now, finally, we get to the validation complexity. And here, this is where the rubber hits the road. And we're talking about AI systems. So actually implementing AI for each of those different projects. And there's a couple of things I want to draw attention to. One is that we can think about, so we want to test out stuff in the short term. So we're creating different kinds of chatbots that are leveraging LLMs and other knowledge tools. And, as we know, in LLMs, there's what's critical is the prompt engineering. And so there's a system that I've used to make prompts better. And this is actually by looking at a number of different AI chatbots, if you will, that are used to help surface powerful prompts. And then, so what this looks like here, just to make it more concrete, is we have a core engine chatbot for a particular AI project. And as I said, this could leverage different LLMs. But then what becomes critical is the prompting that's telling how these LLMs to parse all the data that's existing. So we could feed up different spreadsheets. There could be the model. We basically could do real-time searches, Google search, because LLMs tend to operate in the past. We could feed up other kinds of data, then we could combine it all together, and then we could tell the LLMs how to parse through, first of all, how to think through different questions we're asking, and then how to combine and parse through the data that is being fed into it and come up with advice for the different systems that we're injecting in the short term into to change the system of causality that's driving the organization. When we look at coming up with the adequate or the right kind of prompts, then when we use a system of different chatbots, for example, just hypothetically, suppose we wanted to understand the transition from, say, a future, a market which has possibility in the future, to a market that is robust and is operating due to a maturity of its products, and then finally to a market in which some of the products and dynamics are dying out. So this is suggesting different ways in which to make sense of a market, but then we've got to feed up knowledge about market changes, and we've got to generate different prompts based on the information that we're feeding into a particular set of LLMs to come up with the right kinds of prompts. And then those prompts actually feed what's happening here. So when we're considering validation complexity, the first step is to identify, just to summarize, the first step is to identify the different areas where we want to inject AI in, considering the AI landscape as a whole or the causality landscape as a whole. If we decide that, okay, there's some particular focus projects with customers, then we test that against the model that we've created, the agent-based model that comes up with certain predictions on the overall impact and other dynamics that are important to us that are created from the agent-based model. And this should also predict how things will change over the next 2 years or so. We want to then take a period of time after we've implemented something to see if the rubber is hitting the road. And in fact, if what was being predicted is how it's playing out. And if it is, then great. If it's not, then we need to make adjustments to the model and then have more confidence, test it out again, and have confidence that it's now tracking reality closer. And so then if we're able to have the system, this kind of pipeline, if you will, then that helps us to resolve validation complexity. And so then we have confidence that the model that we've created actually is going to help us decide how to move things forward. And it's putting this whole layer of sense on projects, on AI projects that we might be implementing in the short term. So coming to summary and conclusion here, lessons in crafting AI strategy. So if we have a situation of high epistemic complexity, then causal loop diagrams and agent-based models can be utilized in the service of an AI strategy. Oftentimes, if I go back to the example we started with supply chain management, we start with the linear mapping, and that just gives us a quick idea of how one activity connects to the other. But then what's important is to actually take that linear mapping and make an initial system of causality by seeing all the interactions that happen between one activity and the next and all the rules that are involved. And so we blow out that linear map into a system of causality, of at least a first cut causality. And then we begin to make that more complex by understanding points of view from different actors, understanding measurable results, and creating specific systems of loops that become measurable. We also then begin to get immediate insight into the problem by virtue of understanding the archetypes that exist in the causal loop diagram. We can also, through the net positive and or rather balancing and reinforcing loops, understand whether the cycle time or the anti-fragility is going to decrease or stay the same or increase. And this will right away we'll have insight when we look at the system of feedback loops that exists in a causal loop diagram. When the epistemic complexity is high, then the resolution definitely requires a more sophisticated simulation approach. And my bias has been to use agent-based modeling in favor of system dynamics modeling. The CLD serves opportunities for improvement because it provides insight into existing archetypes, as I said. In an ABM, the corresponding strategies levers are created that simulate the effects of the improvement. So while we have an intuitive feeling from the causal loop diagram, when we actually use a simulation, then we can have a more concrete sense of how a lever or strategy is going to positively impact the organization. The process of creating CLEs and AVMs takes several months. The CLE can be done in, say, 5 to 6 weeks typically, but then the AVM will likely take several months. And what's important is to understand in the process of interviewing is to pay attention to potential bubbles that people exist in or processes exist in. And we've got to be able to surface that. And that's where the mental models and the variation in causal models that I had showed earlier, that's where that can be used. And there's other technologies as well. I'll talk about one of these when we go to the SMB. And then given once the AVM has been created, it becomes possible to run thousands of simulations and understand the kinds of AI strategies that will affect the goals that we're concerned with. Each AI strategy, as I mentioned earlier, can be assessed in terms of some kind of metric that we create that's tracked or that's output by each run of the simulation. And that's how we begin to understand what projects or strategies are going to have higher impact. And that's how we begin to spread things across a roadmap by phases. And there's a number of technologies that exist that are not cost intensive. For example, there's stackai.com, which I've used in actually creating different kinds of AI tools. There's also Insight Maker that allows creation of closed loop diagrams and so on. Now, the question is, what's the applicability to SMBs, to small to medium-sized businesses? Of course, an SMB, it's important to balance financial pressures, but at the same time, there's incredible value in systems thinking, and this should never be ignored because an organization is small. So the practice of getting attuned to archetypes becomes really important, and uh, the organization has to become a learning organization to continually recognize these kinds of archetypes that would exist. There's off-the-shelf emotional intelligence type software that can help teams become increasingly sensitive to mental models that drive perceptions and assumptions. And that in turn is going to give insight into embedded archetypes that often organizations have assumed without even thinking about it. When we're talking about SMBs, the CLE can be created to include key customers. And in this way, any potential marginalizing dynamics at the interfaces can be better managed. Further, rather than take a 5-year roadmap for an SMB, we can do a 1 to 2-year roadmap, and that would maximize short-term investments. And it's important that SMBs get their feet wet with whatever AI they have access to in the context of the CLE that has mapped out their default system of causality. I can't overemphasize that. There also should be an incremental approach to the use of an AVM. So we can start with the AVM that's focused on some aspects of what a small organization is doing and then gradually build it up. And similarly, the metric of success doesn't have to be anti-fragile right away, but it can start with resilience, move to robustness, and then get to anti-fragility. So the point being is that when we're dealing with SMBs, we can take an incremental approach. And as I suggested, there's a lot of inexpensive software that already exists out there that can be leveraged for all of this that makes it easier for SMBs to also embrace causal AI. Thank you.